Hey guys, I'm Nicole.
And I'm Brice.
We're going to walk you through our final project for Electrical 201 lab.
Our assignment was to create a servo system that was a part of the Internet of Things. A servo system is a system that responds based on a feedback created by the system.
By making this system a part of the Internet of Things, we are able to wirelessly communicate with it. And inspired by various Facebook and YouTube videos, we decided to build a prototype for cosplay wings.
We divided our design process into 3 parts. First part was mechanical construction, then the circuit design, and finally the code for the microcontroller.
Mechanically, we tried to keep the moving pieces to a minimum. We opted for a linear actuator as our main motor and then designed the wings to raise and lower by turning 2 discs.
Our goals for the wings were to wirelessly tell the wings to extend and have them stop at the extended position on their own. Then we wanted to be able to reverse the process. For this project, we used the particle photon microcontroller to establish the wireless connection, the embed microcontroller as the processor for our system, and the 10K slide potentiometer to generate a feedback signal that corresponds to the position of the wings.
Additionally, we used an H-bridge to toggle the polarity of the linear actuator and a power bank that provides power for the microcontrollers and a separate power pack that powers the rest of our circuit. Everything starts with the photon particle board. It establishes our wireless connection and relays the signals to the embed microcontroller using the Tinker app from Particle. The embed reads the signals from the photon and the feedback from the mechanical system and then sends a signal through the H-bridge back to the wings to raise or lower them as directed.
The code on the embed uses a continuous loop to monitor the inputs from the photon and the position of the wings from the slide potentiometer and sends a signal through the H-bridge based on which position is true.
After some trial and error, we were able to get the photon embed and wings working together.
This screenshot of the Digilant waveform software in the oscope mode monitors the signals from the forward, which is the blue line, and reverse, which is the yellow line coming from the photon.
Then we check the signals out of the photon and the H-bridge. The blue signal is from the H-bridge, while the yellow is from the photon. Once the linear actuator is in its stop position, the embed prevents the H-bridge from sending an output even when the photon signal goes high.
The yellow line represents the signals from the photon, and the blue line represents the position of the linear actuator as it changes with the directional controls.
Because of the limitations of the software, we can only monitor the 2 signals. The missing signal is from the opposite directional control, but we are still able to observe the change in position from the potentiometer.
As the position is increasing, the forward button is high, and as the position is decreasing, the reverse button is high.
Eliminating as much friction as possible and keeping the connections level proved challenging as we constructed the mechanical system for our wings.
Complications with the code, including getting the values of the inputs to update each time the loop ran and making sure the start and stop positions we designated worked with the structure of the mechanical system.
Improvements we would like to make for any future wings would include a functionality to flap the wings, such that they would extend and retract continuously without the user having to switch them on the app.
This project employs the servo system we've studied and integrates the Internet of Things. We created a modern application that applies concepts that we've studied this semester.